Okay, good morning. All right, and welcome back to Physics 102, which is going to be the after midterm material that we're going to cover. And we're going to continue the topics that we sort of like stopped before the midterm in the topic of sounds and waves. Okay, so we're going to take a look at another kind of waves, which is light. However, we are going to do something that's more like a geometry than like physical summation of like sinusoidal waves or some interference or anything. So we are not gonna do that anymore. So what we are going to do today, it's we call it the optics that is based on geometry. So that's why actually this one we're going to do is a geometric optic. So that means it only requires geometry to pretty much understand the phenomena that we're going to do. Okay, so that's kind of like it will make things quite a breeze today, I think. It's going to be in comparison to other things that we have done. I think this is going to be like a like is a break between midterm and final. So I think this is a good place to uh, sort of like ease you back into the second half of the of the course. Okay, sounds good. All right, so everyone's doing fine, and I hope it's okay to do it online again. We were discussing about this when I and some of you that were at uh, campus last week, just on last Saturday, just before the midterm exam, and we were thinking of. I think if I'm going to do it on campus, actually, I think I'm still about to do it, but we might not do it every week. But I think maybe it's a I don't know. I'm just asking you guys. Is it a good idea if I'm gonna do like maybe some weeks, maybe like every other 2 weeks or so? Would that be okay? So I think maybe that's good in the sense that for some of you that might want to see face to face and have some questions, then you guys can just just meet in person. I think that's good. However, to do that every week, I think it's kind of like for this particular situation right here, it may be a little bit I would say like inefficient in the sense that you might not have questions or anything, and it turns out then you might just be um, sort of listen to the lectures anyway. So I think maybe this is sort of like meet each other halfway. So I think, is that all right? So we just say maybe we'll do one more online next Saturday, and then maybe the day after, the week after that, I can sort of do on campus lecture. Then it's like we have 3 weeks of material or 2 or 3 weeks of material that you might have some questions, or you might have already tried some exercises and homework, and then you have some questions that you want to discuss. I think that may be about the right frequency. Okay, so maybe it's good that for the second half here, we might meet on campus like 2 times. Would that be about right? Yeah, because we have about 6 or 7 lectures to go. So we might do like 2 or 3 weeks of lecture, and then we do one live on campus lecture, and then we come back and do online again for 2 or 3, and then we see each other again on campus, and that will be just right before the final. So all right, so that's, I hope that's all right you got for you guys. Okay, all right, just let me know if you have any suggestions or sort of requests or anything. Feel free to drop me a message, or you can use the chat channel, or you can just line or anything. All right, just let me know. Okay, all right, let's get started, guys, today. So it's quite, so I would say just take it easy today, because everything that we're going to learn today is, I would say no calculus at all, no differentiation, nothing. All right, it's gonna be pure geometry pretty much. Okay, and of course some algebra, which is quite doable. So what we are trying to do today is look at the other two properties of waves. And the best way to sort of like see this or see this or understanding this is using light. That's why I say see this, because that's something that you can actually see visually using your eyes. So we're going to do two more properties of waves, which is the reflection and refraction. Even though you probably have seen this already back in the day that did some science. However, we're going to look in particular for the light system, the system of light. Okay, so you're going to look at the visible light pretty much. So that's why we call these topics the optics, something that you can observe by eyes. And once you know how these sort of principles of reflection and refraction works, then when we're going to look at the cool phenomena here, we call total internal reflection. And then eventually we're going to apply all this stuff to the image formations. So just like this figure showing you. All right. So we're going to explain using these two laws to understand, like, hey, why you see something like this, like you see an inverted image through some lenses and things like that. And that will allow you to understand how to maybe fix your eyesight for those of you that may be nearsighted, or when you wear some contact lenses and all this stuff. All right. So that will be the whole story today. All right. It's going to be quite straightforward, and I think it's kind of nice. Okay, let's get going. Okay, so first of all, what you have seen before, of course, you understand waves quite well now because you have sinusoidal wave to explain some simple single frequency waves. So that's nice. Okay. And then, of course, you can pretty much draw an arrow to represent the traveling directions of the wave. Okay. So that means pretty much you have sort of two ways that you can describe waves now. You can just use arrow to represent the direction of motion of the wave, or you can pretty much like follow the wave and cut the wave perpendicularly, and then you can say where the wave front is at. So that's why it's sort of like the front of the wave, pretty much, right? So that's, you use sort of like that cutaway line to represent where the front of the wave is at, and then you call those lines to be wave front. So if you look top down, so this is the situation that's happening when you have a traveling wave going through an opening. So on the left figure, this is like a simple one. When the opening is quite large, then if you have incoming wave and the wave is going to be pretty much like just keep moving, the one that get blocked, all right, it's not gonna get further, so it's pretty much like diminished and it's disappear. And the one that's go through the opening just keep going. So when you look top down, you will see like a wave traveling to the right, straight forwardly. That is fine. However, if your opening is getting smaller, okay, now you're gonna see some spreading out of the wave. Okay, so now in this case, so what is happening is the wave front will look like a curved one, like this. I'm highlighting it like this. Okay, so you're going from the straight line wave front, which is like a neat and tidy. It's like a sinusoidal wave coming in. But once you hit an opening, then you get some sort of like a spreading out of the wave. So actually what you're seeing over here is we call it's a diffract. So this is a diffraction of wave. So wave sort of gets dispersed out. Okay, so the bad thing about this one is before hitting the opening, you can use the arrow to represent the traveling direction of the wave. You can draw it anywhere you like. That is fine. But once it hits the opening, it's spreading out. So now you need multiple arrow, right? Because like, hey, it's sort of like spreading out. So you don't know which arrows you want to follow. So this is the case that it's a part of something that you need some equations, or maybe some complicated, it's not complicated, but it's like a mathematics that can describe something that actually dispersing out. Okay, so this property of wave, the diffraction of wave, is something closer to the interference of wave. So this means you need some sort of equation or mathematical expression to describe this phenomenon. All right. So the same thing on the right. When the opening getting even smaller, the diffraction is getting even more spread out. Okay, so this is something that we are not going to do. That's a good news. Okay, because actually this one is the kind of thing that we call the physical. It's a physical optics, or it's sort of physical properties of waves. But what we are going to do here is we are going to look at the properties of waves that can be described using purely geometry. So that means it must be the phenomena that the arrow is still good. You can still use the arrow to represent the direction of the waves. Okay, so that means we got just gonna sort of like travel along with the light wave. That's what we are trying to do. So that means we are not going to consider the interference anymore. Just sort of like throw that away because we already done the midterm. Just get that. Or the diffraction that I discussed on top. We're not gonna do it. All right, we just let that one go. So we're going to look at something that you can use arrows. That means you're going to rely on lines, angle, sort of triangle, and all this intersections between lines and all this stuff to understand optics that we about to discuss right here. Okay, that's kind of cool. Okay, so that's what we are focusing on in this lecture, geometric optics. That's what we are doing. Okay, and the good thing is you only need two laws today. The first law is called law of reflection, which is simple one. The reason it's a simple one because it says the angle of the reflection equal to the angle of incidence. That's pretty much it. Nice. A nice thing about this one is like what you see on the left. Okay, so you have a ray coming in from the left. Now you're representing it using just an arrow, right? And of course, in physics, we call it the ray. Okay, so it's a long arrow with the directions. So the ray is there is an incoming incident light from the left, hit some interface or hit the surface or anything, and then it reflected back. So you have a reflected ray or the reflected light. Here comes the thing. It turns out we are pretty much agree when you would like to measure the angle, you usually measure the angle with respect to the normal of that surface or the interface. Okay, guys? So that means every time you see a surface, you will draw a line perpendicular to that surface. And you're going to call it the normal line to the surface. Okay, cool. All right. And then when the ray is coming in, then you make a measurement with respect to that normal line. So this is the one that you want to make a measurement here. That will be your incident angle. On the way out, you also make the measurement of the angle with respect to the normal line. That would be your reflected angle. Okay, and according to the law of reflection, the incoming angle, the theta 1, and the outgoing angle, the theta 1 prime, must be the same. That's it. That is the law of the reflection. Okay, and just to make sure that this law apply everywhere, so you look on the right. So when the surface is smooth, you can see that the law of reflection apply everywhere pretty much. So you can draw a normal line, a normal line, a normal line. So when you have the rays that's incoming, the outgoing rays seems to be in concert. So it means everything goes out pretty much in the same way as it's coming in. So in this case, you get some sort of like a reflection that looks so nice and neat. So we call that it's a specular reflection. So this is the one that you can sort of like experience from looking at the smooth, glossy surface. You are pretty much like see yourself, you see your own reflection through a glossy surface or glossy finish, something like that, right? But on the other hand, if you look at the surface that's sort of like rough, okay? So the law of reflection will apply everywhere anyway. So it means I have to draw a line perpendicular to the surface, a line perpendicular to the surface. Wherever the surface is, I have to draw the line. Just do that. Okay, so wherever it is. However, because now when you look at the surface that has a rough surface, then the reflection pretty much go in crazy direction. So in this case, the reflection looks diffuse because it's sort of like go all over the place. So what you see over here is you're not gonna see like an outgoing ray to be a nice in concert ray. So in this case is equivalent to when you look at the matte finish. Okay, when things like you look at the ceiling, for example, and then it's not glossy anymore, you don't see your own reflection through it. So that will be your sort of indicator that the surface is pretty rough. So you don't have like a glossy, smooth surface. So you don't see reflection easily. So this gives you a clue of something's happening here. It seems like if you have a ray that sort of like all those rays are parallel to each other, and when it goes out parallel to each other as well, it seems like it's preserved the image or preserve whatever is incoming as the outgoing. So you see a reflection nicely. But when the surface is sort of like rough and then your reflections is all over the place, the sort of like the image or the information that carry over from the initial sort of like the source of the light gets scattered out. So you pretty much lose that one. So you don't see your own reflection. Something like this. Okay, sounds good. Okay, so that's sort of give you an idea of what is happening with the reflection and what is happening when the ray are in parallel. So that's kind of nice. That's sort of like it can carry some information along with it without diffusing itself, pretty much. Okay. All right. So that's first law. The second law, this is going to be the law that is the most important today. It's the refraction. So it's come hand in hand with the reflect. Reflections sort of bouncing back. Refract is trying to get through. You want to get through the other side of the interface. So when you look on the right, here we go. So the easiest scenario that could happen is to have an incoming light in the air and try to get through the, maybe in this case, the glass. So you have an interface between glass and air. That will be your interface. Every time that the waves hit the interface, it will do two things. First of all, it will reflect. That's from the law of reflection. So that we are part of it, get reflect out. So that's no big deal. But then if that material is sort of like a transparent, so that means it allows light to get through. So there will be another portion of this one that try to penetrate through the second part of this one or the second material. This is the refracted one. Okay, and we call this phenomena the refraction because it turns out the direction of traveling is changing. Here we go. If I extend the directions of the incoming ray, you will see that the refracted ray makes different directions than the initial incoming incident light. Okay, so that's what we want. We want to know the relationship between the incoming angle. Don't forget, we make a measurement with respect to the normal. Here we go. So every time you have an interface, draw a line perpendicular to that surface or interface. And that's the normal. And then you make a measurement of the ray with respect to that normal line. So that's why the incoming ray is theta 1. The outgoing ray, I'm doing the same thing. So I'm going to have to make a measurement of that angle with respect to normal. So it's this red highlighted angle right here. We call it, let's say, theta 2. And it turns out these two angles are related through something we named Snell's law. That's it. Okay, and this law says is this: n1 sine theta 1 equal to n2 sine theta 2. Okay, so that's how theta 1 and theta 2 are related. So the only thing that we have to explain is what is n, Ajahn. It turns out the n is we named the index of refraction or refractive index. So it's the property of that material. Okay, it's a property of that material. And by definition, it's quite simple. It's right here. The index of refraction, n, is the ratio between the speed of light in the vacuum, and everyone knows it's fixed. This number is pretty much the constants of the universe or something like that, yeah? So we know light travel at about 3 times 10 to the 8 meter per second. So that's about that. It's 30 million meter per second. And then you divide this number by the speed of light in that material. Let's name it V. Okay, so this ratio will give you the index of refraction of that material. Are you guys with me? And in the speaking language, you can call it the N of the material. For example, if this is the glass, you can say, what is the N of the glass? I can say that. Or if this is the air, what is the N of the air? You can say that. Okay. All right. So we are using sort of N so commonly that instead of saying like, hey, what is the index of refraction? You can just say, what is the N of that? I think everyone will understand what it means all the time. So that's nice. So that's what it is. And the good thing about this, I mean, it's not a good thing, but by having this definition of the N, do you notice something here? The N must always be greater than 1 because nothing's move faster than the speed of light. So the velocity V never going to go beyond the C, the speed of light in vacuum. Of course, the best that you can do is probably equal to 1. Yeah, that's possible. And that's happened when the light travel in vacuum itself. That's when the N is 1. So now you can see N in the blank space. When you have nothing at all, there's no gas, there's nothing, it's just pure vacuum. That's when the index of refraction of the air, like a blank air, nothing, not even an air, actually, I shouldn't use air. The N of the blank space is 1. Okay? And the more slowly the wave traveling in that medium, the bigger the N will get. Okay? You guys with me? So in approximations, usually you can approximate that in the air because we fill the air with pretty much like some gases and all this stuff. The N is going to be pretty close to the vacuum. So you can pretty much say in general that N of the air is about 1. That's fine. It's like 1 point something, something, something. It's kind of small. So we can still assume or approximate that the N of the air is 1, very close to the vacuum. But then now, when you are looking at the glass, it's going to make light travel more slowly because light move fastest. It's the quickest that it can move is when there's nothing in their path. So that's why the speed of light is biggest in the vacuum because the vacuum has nothing in the way. Okay, so when you place something in the way, you can put the glass in between, you can put the water, you can put like some polymer, you can put, something. So light have a harder time to go through because something is already in the way. So that's why the speed of light will reduce in other materials, and that make the N grow bigger. So in the glass, N of the glass will be larger than 1. Okay, you guys get the sense of this one? Okay, so I hope if you sort of get this sort of N, the value of the N, that's pretty much it. We're going to use this to explain the property of the material in from the sense of like how fast the light can go. But then we don't want to talk about the speed of light. We don't want to keep saying like, hey, speed of light in this equal to that, speed of light in here equal to those. It turns out we're going to use N instead all the time. Okay, and the reason for that, I think, my theory is you don't want to deal with something that has like a 1 over properties all the time. So because we're going to deal with 1 over V so many times, that physicists just like get tired with divided by things. So they reverse it and name it N. Something like that. So they don't want to deal with the inverse number. So it's just, okay, let's, define the N and then we don't have to divide some things anymore. That's just my guess. All right. So with that, from the definition of the N, so now you can come back and look at the Snell's law. It turns out the product between the N and the sine of the angle in that medium is going to stay fixed all the time. Going through many materials, you can actually keep going if you want. If there is another material waiting underneath, then it's going to be N3 sine theta 3, for example, on and on. All right. Okay. But the point is, you always apply this at the point of refraction. Okay. So you don't have to think about this as like a chain of something. No. You always apply this between a pair of material. Like this one, you look at the N glass and that's it. Snell's law apply at the black dot right there. Okay, with me? And then of course, if this light try to get through the third one, maybe, if there is the third one waiting down here, okay, and then there might be some refraction going on one more time down here, then you apply that at another point. Okay, you guys with me now? Okay, so you can say this is like point P. So at point P, N1 sine theta 1 equal to N2 sine theta 2. And then at point Q, you will say N2 sine theta 2 equal to N3 sine theta 3, something like this. Okay, you always apply Snell's law at a point that's connecting between two materials, and that's it. Okay, nothing complicated. All right. Okay, cool. And then, of course, in some text, but not a lot, because most of the textbook write the Snell's law in the form of N1 sine theta 1. However, there might be some case you want to take the ratio, you want to compare. Okay, so you can flip around a bit. You can say the ratio between sine theta 1 and sine theta 2 is going to be N2 over N1. That is fine. And then you can refer back to this inverse relationship between N and the V. So you can flip it over. You can say, okay, N2 over N1 is going to be equal to V1 over V2. That's fine. But then you can apply V equal to F lambda if you want, because everyone knows the speed of waves depends on the product between the frequency and the wavelength. So you can still do V1 over V2 equal to lambda 1 over lambda 2. That's good. Very nice. But one thing that's missing, you can see that I'm taking the ratio between the wavelength, not the frequency. Do you know why? Okay, that's now I think this is the good point to sort of like take notes going through this one. The reason is because when the light traveling, so you look on the right again. When the light travel from the air to the glass, let's say if I have the light frequency, it's going to fluctuate like this, right? You can not define, you can watch for this frequency F. Let me do like a crazy number, like 10 hertz, which is ridiculous. There's no light with 10 hertz. But what it means is every second, the wave will travel 10 cycles. That's what it means by 10 hertz, right? Right, 10 rounds or 10 cycles per second. So this 10 hertz waves has to go through out here every second as well. You see what I'm saying? Because if you think about this as like a physical waves, like a wave on a string, when you say 10 hertz, it means you have to move your hands up and down 10 cycles each second. And this physical movement cannot go away or cannot be added along the way. So once you generate 10 cycles of wave, that 10 cycle of wave in 1 second has to keep going. It has to go. Just like, hey, like we said, wave never stop. But when you say never stop, mean every 1 second you must count 10 cycles of waves. Same thing over here. Even though this wave go from air to glass, if you're waiting inside the glass and count the number of cycles of the wave, every 1 second you still need to receive 10 cycles of wave, because it's the actual physical movement. You cannot cheat on this one. Okay, you see my point here? So that's why in all of these traveling waves or traveling lights, the frequency stay fixed. It has to be fixed all the time. Okay, all right. So that means every time that you have a velocity of waves reduced, it's going to get compensated by the extended or the longer wavelength, because the F stay fixed in all material right here. Okay, so maybe I talk too much today, but that's pretty much it. When I say pretty much it, because we are going to use Snell's law down until, total internal reflections and everything. Okay, sounds good? All right, let's take a look at how it goes. Okay, so what we have here is a table that's showing you the N of many substances. And this is what exactly happened when you are looking at the vacuum, N equal to 1. In the air, you see that it's pretty close to 1. So let's assume that every time you look at the air, let's say it's about 1. That is fine. What you're going to face quite a lot is Water, of course, is everywhere. The N of the water is about 1.33. So, of course, it's getting more slowly, light traveling more slowly here in the water. The other one that you might see a lot is glass. It's about 1.5 or so. Okay, it's even more slowly. So light having a harder time going through glass. Okay, and now you get like a heavy flint glass or like a super thick glass or no heavy one or sapphire. That's a high quality glass, pretty much. Well, not glass anymore, but that's sapphire. So you get even higher index of refraction, getting even larger value of n. So light travel even more slowly in the sapphire. Okay, and the craziest one that you can see is in diamond. So that's crazy because everyone knows that density of the diamond is one of the highest density material that you can find in nature here. So the light having a super hard time traveling through diamond. So that's why the index of refraction of the diamond is so high. Okay, travel more slowly there. Okay, sounds good. All right. So with that index of refraction of many materials showing over here, so in general, you can get two scenarios. For example, in the top one, that's the one that you just saw. You travel from n, I can call it the smaller n, to a bigger one. Yeah, you go from air to glass. So you're coming from a small n to a bigger one. So in that case, of course, the theta will have to get from a larger one to a smaller one. You guys with me? Because from the Snell's law, it's a product between the n and the sine of the theta. So when you go from small to the larger one, so when n get bigger, the angle here has to get smaller to compensate to give you the fixed product between n and the sine theta. So that's why when you have a light going from small n to a bigger one, then the theta coming from the large one to a smaller one. So you have a refraction that tries to refract toward the normal line. With me? All right. The opposite condition is if you want to go from bigger n and then you travel to a smaller one, in this case, like for example, the light going from glass to air. So of course, the angle will go opposite direction. You coming from whatever angle, the refracted angle will get bigger. So that means your refracted ray will bend away from the normal line. Okay, so those are the two. Okay, so that's pretty much the condition that you're going to face. All right, and of course, if these two having the same index of refraction, you won't see any refraction. Okay, so refraction happens when you try to go through different materials that having different index of refraction in. Okay, you guys still with me today? All right, looks good. Okay, all right, cool. All right, let's get started. And I think by knowing this Snell's law, you are pretty much know how to do everything in terms of the refractions. Quite okay. Let's get going. So everyone still fine with this? Okay. All right. Okay. Okay. ไม่ได้โกรธอะไรอาจารย์นะ Okay. After midterm, yeah. Okay. Let's take a look at the first example here. You have a ray of light strikes a flat block of glass given the index of refraction n. Okay, nice. So let's draw that one. You have a flat block of glass. Let me highlight that. N equal to 1.5. That is the glass. Here we go. The thickness is given. Okay, very good. 2 centimeter. That's fine. At the angle of 30 degree with normal. Okay, perfect. So it's showing you that now you have a normal line. You draw that line perpendicular to the surface or interface. And then the incoming ray is at 30 degree angle with that normal line. Perfect. That's good. Trace the light beam through the glass and find the angles of incident and refraction at each surface. All right, very good. So what I said was we're going to apply Snell's law at a point, the point of refraction. So let me call this point P. So you can say at point P, okay, you can say because this is the air, so we say n of the air is equal to 1. Okay, and the incoming angle is 30 degree. So what I can do is say N air sine 30. See with me, guys? That's done for the first material on top. Now you try to get through the glass. The glass has the N of 1.5. So I would say it's going to be N of glass times the sine of course, is going to be the angle of the outgoing ray somewhere here. So let me call that alpha. You can call it theta, alpha, beta, doesn't matter. But just to showcase what it is, you just say that. That's it. That's how to apply the Snell's law. Simple as that. Okay, so let's sort of plug in the number. N of the air assumed to be 1 all the time. Sine 30 is 1 over 2. N glass given to be 1.5. Then sine alpha is known now. Okay, let me work through this one a bit. So sine alpha is going to be 1/3, I think. Yeah, very good. All right, and then you can punch the calculator. So the alpha will be inverse of the sine of 1/3. Done. That's how you figure out the alpha. Okay, but then there is a bottom interface. Okay, so what you look at the bottom, you can see that it's going to hit the bottom interface, but in this case, because it's just a block of glass, so the upper and lower interface are going to be parallel to each other. So that means it's no big deal, John. I can draw another normal in the bottom, and then the light will eventually refract back into the air. Okay, and then that means at this point of diffraction, let me call point Q, I can apply Snell's law one more time. Okay, but this is a nice thing about this Snell's law. From the look of this one, if the upper angle is alpha, this one is going to be alpha as well. You guys with me? It's just the opposite angle between two parallel lines. So what you have over here is, I can now try to figure out what should be, let me call it the beta, that the light try to coming out from the block of glass. If I try to draw that diagram, look at the Q point, the point at point Q, at Q, starting from the glass. So you say N glass, that's your incoming ray, sine alpha. You guys with me? Okay, right here. Yeah, at this point Q, incoming ray, making the angle alpha with respect to normal. So N glass sine alpha is going to be equal to, on the way out, now you get out to the air. So you back into the air. So it's going to be N air, N of the air, times the sine of the beta. With me? Cool. All right. However, บอกให้อาจารย์ take a look at this. It looks exactly the same as the first equation up top. See that? So now you don't even have to do anything. You can just say right away, of course, the beta must be 30 degree. That means it looks symmetric on the way in and on the way out. Snell's law look exactly the same. So because the incoming angle is 30, the outgoing angle must be 30 as well. So that means what I'm trying to say over here is, I'm not drawing this correctly. I have to draw something like this. Let me do this. It's gonna look something like this. Okay, here. Let me extend this line out. So the outgoing ray will make 30-degree angle with the bottom interface, and it's going to be parallel to the initial direction of motion right there. Okay, cool. All right, so nice. See, not bad. So these two parallel. Nice. Well, I'm not drawing it nicely, but they are parallel. It looks like it's diverging, but well, okay, my bad. Okay, you guys can draw a better figure than mine, I guess. Okay, good. Okay, looks cool. So at least this is the first example just to showcase how to apply Snell's law. Okay, you apply a Snell's law at a point of refraction. That's it. Okay, and look for the incoming angle, the outgoing angle, looking for the end of the incoming material, and looking for the end of the outgoing material, and that's it. Okay, so that will be the application of Snell's law. Okay, let's get going. Okay, any questions so far? Looks good. Okay, it's kind of like going pretty well here. Not complicated. Try again, one more. When the rectangular metal tank in the figure is filled to the top with an unknown liquid. All right, so you guys should try this one. Okay, this is the level of the question in the exam about so, but it's not difficult at all. Once you finish this one, you'll see. The observer O, with eyes level with the top of the tank, can just see corner E. All right, so this is a good example that I'm going to explain about what is going on with the image formation in your eyes, or actually in your brain. That's later. Okay, so a ray that refracts toward the O at the top is shown in the figure. So what it's saying is there is an image of the corner of the tank at point E over here. Okay, so when you say, when you want to see something, there must be some light hitting your eyes. That's when you see things, right? And it turns out, because this light generated from the corner of the tank, and it's just get going, try to get to the top surface of the tank, but then it's go through refraction, and accidentally the refracted ray making a 90-degree angle with the normal, and it hits your eyes that is just waiting right here, that when you try to look at it. So that's why this allow you to see the corner of the tank without actually aiming at the corner of the tank directly. Okay, you guys with me? Yeah, cool. So this is the phenomena that you see every time that you try to look at the bottom of the tank. All the time you will see that the bottom of the tank appear a little bit sort of like shallower. It's getting sort of like the bottom of the tank is getting, raised up. Or when you look at the straw, when you have a straw in the cup and something, and then if you look from the top, you will look at the straw look distorted a little bit. It looks shorter, it's shortened down. That's due to the refraction of light. The light underneath the water, when it tries to get out into the air, it has the refraction. And once it gets into your eyes think that the source of that image coming from directly straight in front of you. And that's make it a little bit sort of shortened. It's shorter than normal. Everything looks shortened. Okay, so this is an extreme case that, well, it's not going to happen in realistic scenario. But assume that if the light actually refracts at 90 degree, and then you take your eyes, okay, waiting at the level of the surface of the tank, you will be able to see the corner of the tank, because that's where the light is coming from. Okay, sounds good. All right, but this is exaggerated, of course. All right, everyone shouldn't be able to do this exactly at 90 degree. That's a little bit too much. Okay, but that's in theory. Okay, so if the dimension of the tank is all given, the depth, the width, and all this stuff, what should be the index of refraction of the liquid? Everyone try this. I want you to try to set up the Snell's laws equation, and let's see what you are setting up matches what I'm about to write the equations. So everyone applies Snell's law at the point of refraction. Do it now. Go ahead. Like, think of it like a workshop or something. All right, here we go. Got that. Okay, the way to do this, every time, don't forget, you will apply Snell's law at the point of interface or the point of refraction all the time. And that point is right here. Oh, suppose, here, let me draw it. Here. That's where the light refracts. It's right there. So you can call point P, for example. Okay, go ahead. So you say at P. So what happened? First of all, because you don't know what is the index of refraction of this liquid, so let's assume it's N sub L, N of the liquid, let's say. And because every time you have an interface here, let me draw a line here. That's your interface, that orange line right there. You would love to draw a normal all the time. So that's going to be your normal, which of course in the figure it's already give it to you. So that's good. Okay, so that's normal. So your incident angle will be this angle right here. That's theta 1. Okay, you guys with me? So that means for the incoming ray, Snell's law gives you N sub L sine theta 1. Okay, now outgoing, the outgoing ray is parallel to that interface. So it means at 90 degree. Okay, so the outgoing ray, the N now is going to be N of the air. So let me put the subscript A for it. N sub A, which is 1. We agree to use 1 for the air. So it's going to be N sub A. Now it's going to be sine 90 degree. That's it. It's done. That's how to get, that's how you get the equations that relate the theta 1 and that's 90 degree through the N, Snell's law. And the rest now is easy because sine theta 1, you can figure it out. Okay, when you look at this one, you say, John, sine theta 1 is just opposite over hypotenuse. The hypotenuse is just Pythagorean between L square and the D square under square root. So actually sine of the theta 1 is going to be L over square root L square plus D square. All right. However, the numbers is kind of like very kind. L is 80 centimeter. D is 60 centimeter. So everyone knows the hypotenuse will be 100 centimeter. That's nice. Okay, so that means the sine theta is going to be 4 over 5. 80 over 100. All right, very nice. So you plug that in, then the N sub L is going to be N of the air is 1. Sine 90, that's also 1. Divided by sine theta 1, which is 4/5. So that's it, 5 over 4, and you're done. That is your N of this liquid right here. สนุกไหมอันนี้โอเคไหม Pretty good. And one thing that you can sort of use to be your sort of error checking point is this is good. It's greater than 1. Nice. So whenever you calculate N, the final number should be bigger than 1 in general. Okay, so sometimes when you calculate the N and then you get like a fraction of a number, then I mean a fraction of 1, then that doesn't make sense. Okay, it has to be larger than 1. It couldn't be smaller than 1. All right, so as you can see now, I hope by showing you 2 examples, see, is geometry. You use Pythagorean theorem, you use trigonometry, on and on, to figuring out things, and everything based on Snell's law. Okay, so start seeing why this one called geometric optics. Try again. Okay, everyone try this. So now you have 2 interfaces, okay, from the air to the oil, and the oil to the water. Okay, and then you have a light beam. It could be like a laser beam, for example. Shine the laser beam through the air, get through the oil, and then try to penetrate down to the water. So you have sort of like a layer of the oil on top of the water, something like that. And then the figure say that the theta is 20 degree. Okay, the normal lines, with respect to the normal line, which is good, they want you to figure out the angle of the theta prime. And, oh, I'm sorry, the 20 degree is the angle that is on the interface between the oil and water. Okay. So they want you to figure out what should be the theta and the theta prime. Okay. And now everyone should be able to do this quickly now. So let's start from the closer one that can be seen is, let me call the bottom interface. The light hit point P and try to refract into the water. So I'm going to start right there. And you'll see that I can do it very quickly here. Let me do it here. I'm going from the oil to the water. So I can say end of the oil, side 20, you guys, equal to end of water. Let me use subscript W there, sine theta prime. And that's it. I'm done. You guys with me? Okay. So every time that you look at this Snell's law, I suggest that you think of it as an application at a point. So that is my sort of like, I would like to emphasize this point so you won't get confused. Okay, so like this. And that's it. So end of the oil is given to be 1.5. Sine 20, okay, you can punch the calculator for me. End of the water, it's supposed to be somewhere here. You can go back and look at the water, 1.33. But in the exam, of course, all the n will be given, so you don't have to sort of think too much about it. And then you should be able to figure out what should be the theta prime from here. Okay, try one more time. Of course, if the angle with respect to normal at point P is 20 on the incident one, then it will give you 20 up here as well, opposite angle. Okay, so that allow you to calculate another point of refraction. Let me call point Q on the top. So at point Q, let me do it just the same way. You can do end of the air. Let me use subscript A for that. And sine of the incident angle, that is your theta at the top, will be equal to, and then you can see down here is once again end of the oil and sine 20. And that's it. You should be able to, okay, end of the air is 1 automatically. So I should be able to say sine theta is going to be 1.5 sine 20. And then you should be able to figure out what should it be for the theta. Done. Okay, so I hope it's straightforward to apply Snell's law everywhere. Just think of it as application at a point of refraction. And I think things will be quite clear. I don't know if it's clear or not, but that's what it is. Cool. All right, very good. So once you have this, now we're going to take a look at one application of this. And actually you use it every day now. Okay, this application is the total internal reflection. And this is kind of cool. When I say cool is, look at this one. Now let's sort of think along with me. Now everyone knows now that if the light going from high end to a lower end, okay, you follow my idea here. So let's say down here, the end is big. Okay, this is the big end. And then you try to take the light from big end to a smaller one on top. So this one is smaller. Okay, so you go from large end to a low end. The light will refract away from the normal. Okay, you guys stay with me, yeah? Okay, so look at this one, for example, the ray B, see, it will refract away. Ray C is refract away. Ray D, it will refract even bigger. So the larger the incident angle is, the bigger the outgoing ray is going to become. Okay, you guys with me, yeah? Because it's the refraction away from the normal. So once you increase the incident angle, the refracted angle will get even bigger all the time when you get the light from the large end to a small end interface. And then there will be one case that's happening. if you keep increasing the incident angle until you hit one angle that make the outgoing ray to be at 90 degree. My question is, what will happen next if you keep increasing the incident angle? You guys with me? Yeah. The answer is the light will have nowhere else to go anymore, because this is already at the critical case when the refracted ray is already at 90 degree. You cannot have any angle greater than that anymore, because that's it. So that means beyond that incident angle, you will get pure reflection. So that means if you keep increasing your incident angle, what you're going to get is now you're going to get pure reflection here. You get pure reflection there. And that's what we say. That's a total internal reflection. So it means it's going to reflect back into the initial material or the initial medium. The angle that makes the outgoing ray to be at 90 degree, we call it the critical angle theta sub c. Does it sound cool? I don't know cool or not, but that's what it is. So it means once the angle of incident is beyond the critical angle theta c, theta sub c, that's when you're gonna experience the total internal reflection. But then you say, hey, Ajahn, what does it mean by total internal reflection? So you can think of it like now this interface here behave like a mirror because it gives you reflection, no more refraction, yeah? So that means once you hit this total internal reflection phenomena right here, the interface between water, in this case, like, you know, water and glass, water and air and all this stuff, behave like a mirror. And that's what the figure on the right showing. You sort of experience all the time when you like maybe diving down into your pool and then you try to look up. So it means right now your eyes is in the water and then you try to look up into the air. So it's exactly the same as this scenario. You going from the big end to a smaller end, which is the air on top. You are in the water. But then at this angle, okay, so there will be a light coming from the back, okay, of, in this case, like maybe some swimmer over here. And then the light actually try to get through the air, but it cannot. Because at this angle, it turns out you get total internal reflection. So you get reflection back to you, which is, well, I try to write this one in 3D, but that's what it is. So the reflection is try to, you know, it's try to, well, this is going to be better here. Bam, and then try to reflect to your face, to your eyes. You know, I don't know. Well, it's supposed to be perspective here, but you get the point. The point is the light cannot get out into the air. It get reflect, not reflect back to your eyes. So that's why your eyes can see the reflection right here on top. That's what it is. Okay, I shouldn't draw this. It looks bad. But that's what it means. Every time you see reflection like this, that's you already hit the total internal reflection condition. Okay, sounds good. All right, so I hope this one sort of like clearly related to what you probably have experienced before. Okay, so how can you figure out this theta sub c over here? How can you figure out the critical angle? Okay, so the critical angle is easy to find. The reason is because it happens when the outgoing or the refracted ray makes the 90-degree angle with the normal, correct? So all you have to set is, okay, you start from, let me call this N1. You try to get to the N2. Okay, and the condition now, you know that the N2 is supposed to be smaller than N1. Okay, so this phenomena will happen only when you try to get from a bigger N to a smaller one. So you say N1 using the Snell's law applying at a point. So let me highlight black again. So at point E, that black dot right there, the incoming has an N1 sine theta. We're going to call them the theta sub c, right? The critical angle. So let's do theta sub c is going to equal to outgoing ray, which is going to be N2. That's the second medium. And then you just set the refracted angle to be at 90 degree. And everyone knows sine 90 is just 1. So that's it. This is how you calculate the critical angle. It's just the sine of the critical angle equal to the ratio between n2 over n1. And because n2 is always smaller than n1, of course, this ratio is always less than 1, which is perfect. That's the requirement for the sine of the something. Yeah, the sine value never go beyond 1 and never go below -1, on and on. So that's why the total internal reflection from the mathematical perspective over here, you say, is never going to happen when they try to have the light go from the smaller one to a larger n. It's never going to happen. It will happen only when you try to travel the light from the bigger n to a smaller one. Try to get out of something. Okay, sounds cool. All right. So, and that when I say you use this one every day, because I think right now everyone is using optical fibers. Okay, and that's what it uses in the optical fibers. The reason that you can use the fiber to direct light and of course send the information or the data or the stuff, because you rely on the total internal reflection inside the glass or the plastic or the polymer that they use in the optical fibers. Okay, and that's it. Use it every day. All right, but of course you might not be able to look into the internet fibers. What you can look at is maybe from a toys or from the decorative items like this. So if you go through maybe Chatuchak or whatever, I don't know if they're still selling this or not, but if you see something like this that look like a plastic, it's kind of like translucent a bit, transparent a bit, and then you can see that it's sort of like sparkling toward the ends of these fibers or the stuff. It used the total internal reflection to bring the light source. To bring the light from the source, which hidden here somewhere. Oh, it's hard to see. It's the source of the light somewhere in here. Okay, and it's just gonna travel along the fiber, and then eventually, when you get out to the other end, it will just shows up here. Okay, it looks kind of nice, like a mini light bulb, something like that. All right, but anyway, we use this optical fibers every day now. Yeah, and it's much better than electrical signals in the you guys use ADSL before, right? So the technology that comes before the optical fiber is going to be the telephone lines data. So you take the data along the telephone lines, and that has some big limitation because the amount of data that you can squeeze into an electrical wire is not as much as light. Okay? Light, it's non-interacting, so you can put a lot of stuff in a single line of fiber. Okay, but when you use electricity along the conducting wire, that's not a lot of stuff because electrons are repulsive. So you cannot squeeze a lot of data into a single electrical wire. Okay, so that's now we all use fiber optics now. Okay, cool. All right, so that's what it is. However, from the perspective of Snell's law, there's nothing new, right? Because all you're applying is once again Snell's law. So that's why I'm saying happy. Once you get to know how to use Snell's law, you can pretty much do anything you like about the refraction and an interface. So let's take a look at one example right here. So we have a 600 nanometer light. Calculate the critical angle for the following materials surrounded by air. Okay, so let's try it. So if you have a diamond, so at the interface of the diamond, so let me do this. This is diamond. So let me put N sub D. Let me put DIA then. End of the diamond. And then you try to get out into the end of the air. You want to figure out the critical angle. So let me draw you the diagram in full detail here just to sort of review what we have done here. So if the light try to get out from this diamond and you want to figure out the critical angle, so it's going to hit at some angle and it makes the outgoing ray to be making 90 degree with the normal. This is a scenario that we're talking about, the critical angle calculations. So at a point of refraction, once again, I can call this point P again. So at that point, I'm going to start with N diamond sine theta C equal to N air sine 90. See that? So actually, I don't need to actually memorizing this formula at all because I can always starting from Snell's law and set the refracted angle to be at 90 degree. And then the incoming angle is automatically the critical angle. Sine 90 is 1. So the sine theta C is in air is 1. In diamond. So if you look back in the table, that's the one that I commented before. The diamond is about 2.4, about so. Okay. So from here, you can figure out what should be the theta sub C. All right. Oh, cool. I can do that one more time with glass. Everything look exactly the same. I will hit it with some angle. The outgoing will be 90 degree. Scenario look exactly the same, except now you're going to get end of the glass and end of the air on top. But equation will look exactly the same. Let me call this point Q. So at point Q, N glass sine theta critical. So let me call prime here because so you won't get duplicated with whatever theta C that we use in part A. N air sine 90. Very nice. Okay, and of course, everyone will be able to calculate this to be 1.5. That's end of the class, approximately about 1.5. So the theta C prime will be equal to what? Now, what I want you to try is just to check that you know how to use your calculator. What should be the theta C or theta C prime? Can you punch the calculator and make sure that you know how to do the inverse sign? I think maybe that's the critical part. Because in the exam, I have seen many of you just give the wrong answer. You have to make sure that in your calculator you set to be degree or radian. You have to make sure that you set that correctly and answer your questions sort of correctly as well using the correct units. Okay, but of course, in general, for this one, just to communicate better, usually you use degree because we are not really doing mathematics of a circle or anything. So usually you try to answer in angle, in your angle in degree. All right. But there is another point that I want you to make. Okay, everyone, try calculating this. I'm doing it as well. So let me do inverse sine of 1 over 2.42. Okay, 2.4. Oops, sorry. 2.42. Okay, it's about 0.413. And I'm going to do inverse of that. Okay, inverse. There you go. It's about 24 degree approximately. Get 0.4, but that's approximate. Okay, you guys calculating with me right now? เฮ้ยปล่อยจานทำคนเดียวนะเฮ้ยช่วยกันหน่อย All right, 1 over 1.5, 0.66. Okay, so I'm going to do inverse of that. Inverse 0.66, 41 something. Okay, approximately. All right, I don't know you guys with me right now. เฮ้ยทุกคนยังอยู่ใช่ไหมเนี่ย ทุกคนเงียบมากเลยไม่ได้โกรธอะไรจานนะ Okay, all right. Okay, very good. So what's the point? Why I really want you to see these angles? Do you notice something here? The critical angle between air and diamond is 24. The critical angle between air and glass is 41. This is the reason why diamond is more sparkling. You see that sparkling? All right. And of course, if you take the glass and then you try to do the diamond cut with the glass, okay, that thing will not going to be as shiny, sparkling as the real diamond. That is because for the diamond, it takes only 24 degrees for the light to get reflected back. And every time you look at the sparklingness and all the stuff, it means the light enter the diamond and try to get out. It doesn't want to get out the other side. It's get back towards you. So that's why you look at it as like a reflection, sparkling and all the stuff. But if it's the glass, it takes larger angle to get total internal reflected back. So that's why big portion of the light actually get through to the other side of that glass block. You guys with me? All right. So that's the reason why maybe Swarovski make of a sapphire or the stuff has the end to be larger than glass, but not, of course, not going to be as big as the diamond. It's quite sparkling for the Swarovski crystals, all that stuff. However, it's not going to be as good as the diamond. So that's why maybe diamond is more valuable and all this stuff because of the hardness, the density, and this now you give it gives like a nice optical properties. Yeah, it's very good. You know, when combine it with the diamond cut and all the stuff, it's very shiny, okay, in comparison to other materials. Okay, sounds good. All right, so that's give you another reason why the diamond is so sparkling. And actually, this gives you the reason why the shape of the diamond has to be, well, I think I forgot to squeeze that one in, but when you look at the shape of the diamond, there is a reason why it has to be this shape all the time. Because the angle that it design and all this stuff, it depends on this critical angle right here. So that's why usually you have like a sort of like a pretty fixed sizing aspect ratio and all the stuff, the angle and all the cut that you're supposed to make with the diamond. That's to optimize the reflection and coming out of it. Okay, all right. So that's a physics behind it. All right, cool. Okay, try again. So this is more like a question that is going to sort of like, you know, give you some idea what kind of question that it should be in the exam. In the figure, a layer of light is perpendicular to the surface AB of glass prism. Okay, so you have like a block of glass that has like a sort of like a cylindrical shape with the triangular cross section. Find the largest value of the angle phi so that the ray is totally reflected at the surface AC. And if the prism is immersed in air, so that's normal case, or you dump this into the water and then you want to calculate that phi. Okay, so A and B are not going to be much difference, okay, because it's just the incoming N in part A is going to be air. The incoming N for the part B is going to be water. That's all. Okay, so let's start with part A. First of all, this is a good one in the sense that what happening on the surface AB, guys? The answer is nothing. The reason is nothing because you hit it perpendicular to the surface. So that means you are going along the normal line right here. So this means your incident angle is 0. Incident angle equal to 0. So when the incident angle is 0, Snell's law is give you everything 0. So the light will just keep going straight. That's what happened. Okay, this one just to make sure that, okay, you see the condition when the light hits the interface perpendicularly, it just keep going straight. No refraction or anything. Now, once it hits the surface AB, now that's when the refraction starts to happen. So once again, I'm going to start with drawing a normal line. And because you would like to see what is going to happen when things get totally reflected, so I'm going to take the condition of outgoing ray to be at 90 degrees. You guys with me? That's when things start to reflect back. Okay. And then you apply the Snell's law at a point of refraction. let me call once again that point P. So let's say at P, the incoming is starting from end of the glass. Let me put, oh, it's hard to see. End of glass. And it's trying to get out to the air, n sub air, that's equal to 1. End of glass is 1.5. So at point P, Snell's law say in glass, okay, now it's going to be sine of the incident angle. Don't forget, we always measure the angle with respect to normal. So it has to be this angle right here that you're going to put into your Snell's law equation. Okay. Now, the question asks you in terms of the phi. Phi angle is right there, so it must be this angle right here. So the the yellow angle right here is going to be 90 minus phi. You guys with me? Okay, very good. Okay, so good. So you put it there. So it's going to be incident angle is 90 minus phi. Now that's done on the left-hand side. You equate that to what happening on the outgoing refracted ray. You're going to the air, N sub A. And then because you take everything to be about to go total internal reflection, so you set the outgoing ray to be at 90 degrees. This allow you to figure out the phi. And of course, sine 90 minus phi equal to cosine of the phi. You guys remember this property here? Okay, when you do sine 90 minus something, you can use the co-function of that sine, which is the cosine. Okay, in glass is 1.5, in air is 1. So you say cosine of phi is 1 2/3. This is 1 over. And that's it. So you can say phi equal to, you just do inverse cosine of 2/3 and you're done. Okay, very good. And of course, in part B, everything will look exactly the same except you immerse everything in water. So the only thing that you're going to have to change is this n sub A right here. So instead of use n sub A, you just use n sub W for water. And it could be like, let's say 1.3, for example. But everything else look exactly the same. So for that, you're going to say n glass sine 90 minus phi equal to n of water sine 90. No difference. The only difference is you just substitute in air with n of the water. Okay, cool. All right. So I hope by showing you, I think we have done quite many examples here. You see that it seems like there's only a single approach to the Snell's law. And I just want to emphasize again, try to think of this Snell's law to be the equation that can be applied at a point of refraction. By thinking in this way, it seems like you're not going to get confused when things get complicated. Okay, because you always apply at the point of the interface all the time. No matter how complicated the questions might look, you always apply this at one point at a time. And then you have to move on to the next interface, next point, and then you do the Snell's law. And then you might see some connections. That's good. Okay, but usually every time you try to apply this one, you apply it at a point. Okay, sounds good. I'll keep saying that. Is that good? I hope it's good. Not bad today. Okay, let's do one more, guys, and then I think we can take a break after these examples. All right, I think this is going to be the upper limit of things that will show up in the exam. I don't think the exam question will go more complicated than this one anymore. All right, this is it. Okay, give it a shot. Okay, this one is try to mimic what's happening in the optical fiber. Okay, just like send a light and then they try to stay in, something like this. Okay, so in the figure, a light ray enters a glass slab at point A at some given angle. Okay, theta 1 is given to be 45 degrees. And then it undergoes total internal reflection at point B. Okay. What minimum value of the index of refraction of glass can be inferred from this information? Okay. The reflection at point A is not shown. Okay. So actually, in all the problems that we have seen, okay, don't worry about this one, because every time that you hit the interface and you get some refraction, there will be a portion of light get reflected back all the time. Okay, so this is something that's always the case. So every time that you see this, there'll be, okay, this is hard to see, but like here, this is a good one. See, so every time that you have refraction, you always get some reflection anyway, all the time, a little bit. Okay, like over here, you get some refraction, you get some reflection here back all the time. So every time that the light try to change the medium from one to the other, there will be a portion of the light that get reflected back. Of course, except when you get total internal reflection condition, then you get total 100% refraction. But if not, if the light can actually refract into the other material, there will be a portion of it that get reflected back. And this is the reason why when you standing in front of the glass window, even though you say the glass is transparent, but you can always see your own reflection through the glass. Yeah, you always see a little bit of yourself, like maybe 5-10% of your reflection through the transparent glass, and that portion of that reflection give you that reflection of yourself. Okay, all right, so that's all the time. Okay, you pretty much you cannot avoid it. Every time that there is a change of the medium, sometimes some of the light get reflected back all the time. So there'll be like a faint reflection going on here, back out. Okay, but for us right now, we are focusing on what is happening on the refracted beam. Okay, so what should be the index of refraction if you want the total internal reflection to happen? They want the minimum value. So it means if you have a bigger value, then of course you guarantee to have total internal reflection. They just want to get like a minimum conditions when you hit it at 45 degree. All right. So once again, let's do this and be careful on here. It's pure geometry. So make sure that you get the geometry right. Let's look at what happened at point A. Okay, what happened, guys? So now you should be able to do this one quite okay now. You're starting coming from A. So let me use subscript A for that. And then you try to get to the glass. Let me put subscript G for that. So at point A, n sub A sine theta 1, you guys with me, yeah? That's from the first upper medium in the air, is going to be equal to n sub glass. That's your second medium. You're going into glass. And of course, it's going to be the sine of, okay, let me use alpha here. Don't forget, the angle has to be with respect to normal all the time. So it's going to be sine alpha. Nice. Okay. So what's known? Let's substitute it in. NA, N sub A, that's known. That's the air. Sine theta 1, that's known. Theta 1 is 45 degree. Now in glass, that's what we try to figure out. Sine alpha, of course, we don't know what the alpha is supposed to be because we don't know the end of the glass. So let's keep this as a first equation. Let's move on to point B. Okay, because now you would like to see the condition that you start to get the reflection. So I'm going to turn this one into the condition that we can figure out is, let's take the refraction at B to be the condition when you get total internal reflection right here. You guys with me? Because you want to get things started here. You want get the ray to start doing the total internal reflection. So you analyze the condition when the outgoing ray, the refracted ray, is making the angle of 90 degree with normal. That would be your starting point that the total internal reflection start to happen. Okay, you guys with me, yeah? So at point B, what will happen here is, of course, now you're going from glass out into the air. So you start from the glass here, okay? So you get n sub G, you guys with me? Now I'm in the glass. making the angle. Which angle, guys? Don't forget, it has to be the angle that measure with respect to normal. So it has to be this angle right here. Let me call it beta. Okay, I hope you see when you try to put the angle into your Snell's law equation, it has to be angle that make with respect to the normal line all the time. So it has to be beta right there. Okay, that's done from the glass side. Let's get to the air. So when it tries to get out, you're going to get end of the air. And then you say that you want to make this angle to be at 90 degree out. Yes. Okay, very good. So let's substitute things that you know. In glass, don't know. Beta, don't know. End of the air is 1. Sine 90 is already 1. So that's your equation number 2. Looks good. Almost done, guys. The only thing left here is you can see right away alpha and beta are related. By looking at this triangle right here, the alpha plus beta must be 90 degree. You guys with me? Because you have a right triangle over there. So you can say that the beta is 90 minus alpha if you want, which is cool. So what you have over here is I can turn everything into just the alpha and n sub g, end of the glass. So let me redraw, sort of write this equation one more time. So it's going to be sine 90 minus alpha. And everyone knows, once again, every time you have sine 90 minus alpha, it's going to be cosine of that alpha equal to 1. That is your second equation updated. Let me put it to be 2 stars. All right, and that's it. So you have 2 equations with 2 unknowns. You can figure out everything. So the easiest one for you to do is just take the ratio between the 2. So what I can do is take equation number 1 divided by equation number 2 stars. Okay, let me show you what it means here. N sub g sine alpha divided by n sub g cosine alpha, yeah? So I take the side that has the sine and cosine to be in the same side, and then equate that to sine 45 over 1. Okay, very good. So the nice thing about this one is the n sub g will cancel, and you're going to get tan theta here. Sine over cosine is tan theta. And from here, you will know what should be the alpha. But you need calculator now. อันนี้อาจารย์ก็ไม่รู้ค่าเหมือนกัน so you say tan of the alpha equal to sine 45, which is maybe root 2 over 2. And then you can punch the calculator to figure out the alpha. Once you get the alpha, then you can just substitute this alpha back into whatever equation 1 or 2 stars. That's up to you now. Okay, once you know alpha, plug it back in, you can figure out n sub g, and then you're done. พอไหวไหมอย่างงี้ not too bad. Okay, but as I said, this is going to be the upper limit of the questions. I don't think the question in the exam will be any more complicated than this one. I think this is good. Okay, guys, if this is all right, then I think this is a good place to take a break. Sounds good.